Okay, so now we begin the section on 16.2 on electric force. Only two learning targets that we're going to look at today is just the electric force using Coulomb's law, and then comparing the electric force to the gravitational force. So read through 16.2, just a few pages there, and then we'll take a look at some problems when we're done. So first thing we want to look at, charges can influence other charges through the electric force. How is this force similar to and different than the gravitational force? And really the easiest way for us to look at that is just to look at the equations that describe both. And you can see there are quite a few similarities. They are both the same general form. You can see that the gravitational force is computed by capital letter G times the product of the masses divided by the distance between their centers squared. And the electric force has a different different constant rather. It's called the Coulomb constant. It uses a product of the charges that are on each object, and they're also then divided by the square of the distance between them. So probably the first thing to notice is that they are both inverse square laws. And so from that standpoint, we're going to say that both of the laws depend on the distance between their centers, and they are both inverse square laws. So if we increase the distance, we decrease the amount of force, and that does so according to the square of that distance. Another thing that's similar is that the proportionality constants were found in similar ways. Capital letter G was found through the Cavendish experiment, and you may recall that we talked about that back in chapter 7. And then the Coulomb constant was found by a gentleman named Coulomb, and he used a torsion balance, a very similar kind of experiment to determine the value of K sub C. And another thing that's similar is that they have a product of two physical quantities, either the charge or the mass on the objects. And so those are really the ways in which they're similar. But there are some differences. First off, K sub C is a lot larger than G. And we'll look at some of the examples. We'll see the relative size of that constant is very large compared to that constant. Another thing, the gravitational field strength is fixed, but the electrical field strength can be changed very easily. Just depends on how much charge we actually put on those objects. And so we'll look at that in section 16.3. And then another major difference is that gravity can only be attractive. So these two objects can only attract each other through the gravitational force, whereas the electric force can be attractive as well as repulsive. So these two would attract each other because they have opposite signs, and these two would repel each other since they have similar signs. Let's go ahead and take a look at a few examples. So here we have an electron and a proton of a hydrogen atom. They're separated on average by a distance of 5.3 times 10 to the negative 11 meters, and we want to find the magnitudes of both the electric force and the gravitational force that each particle exerts on each other. Now the hydrogen atom is the simplest of all the atoms. These two things are attracted to each other. The proton and the electron attract each other. There's quite a bit of difference in masses here, and so in reality the electron is what accelerates the most as it moves around the proton. And this is somewhat of a simplified version of an atom. It doesn't really just move in a circular orbit. It really is more of like a cloud here. But what we want to do is we want to determine the magnitudes of each of those forces of attraction, one due to gravity and the other due to the electric force. So let's go ahead and do the gravitational force first. The equation that would describe the gravitational force between these two would be F sub G is equal to big letter G, mass of the proton times mass of the electron, divided by the radius or the distance between their centers squared. We're going to go ahead and just plug in those numbers there. Again, you don't need to memorize the mass of the protons or the mass of the electrons, but this is what they are, very small numbers. Then when I divide that by the distance between their centers squared, what I get is a force of about 3.7 times 10 to the negative 47 newtons, so a very, very small amount of force. And that should make sense because they have very small masses. Now, we also want to go ahead and compute the electric force. So what I'm going to do is use the equation to describe the electric force is Coulomb constant. times Q1 times Q2 all over r squared, and these Q's are the amount of charge that are each one of those objects. Well, the Coulomb constant is 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. And then the charge on the electron and the proton, they're both 1.6 times 10 to the negative 19. The electron is negative, the proton is positive, so it's going to be an attractive force. And they're separated by the same distance as they were over here. And when I compute this force, we can see that it's 8.2 times 10 to the negative 8. Now again, a very small number again, but what's really striking about this is just how much larger the electric force is as compared to the gravitational force. This is 10 to the negative 8. This is 10 to the negative 47. If I were to take the ratio of those two forces, I'd see that the electric force is about 2 to the 39th times bigger than the gravitational force. It really just reinforces the idea that the gravitational force is a very, very weak force, and the electric force in this case is just so much larger. That is obviously the dominant force that holds the electron and the proton sort of together, and the gravitational force is essentially non-existent compared to this. So again, just shows you the size of that electric force. Let's go ahead and do a few more problems here. Two electrostatic point charges of 60 microcoulombs and 50 microcoulombs exert a repulsive force on each other of 175 newtons. We just want to determine what their distance is between the charges. So again, I'll start with the Coulomb equation. I'm going to go ahead and change that equation around for r. So I'm just going to multiply both sides by r squared and divide both sides by the electric force, and I take the square root. When I go ahead and plug in those numbers to get my value for r, I will see that the distance between their centers is about 0.39 meters. And again, just some algebra that's needed in order to go ahead and do that. Now, this next problem is quite a bit more involved, so I want to give myself a little bit more space here. Here I have two identical conducting spheres with their distances about 30 centimeters apart. So I have a positive charge and a negative charge, and they're located about 30 centimeters apart. So this distance between their centers, about 30 centimeters, or about 0.30 meters. Now, based on the charges that are given to each of those, we'd like to determine the electric force exerted on each other. Well, that's fairly easily done with just a Coulomb equation. So in the beginning here, we have 8.99 times 10 to the 9th times 12 times 10 to the negative 9. That's the charge on the positive sphere. That's a negative 18 times 10 to the negative 9 coulombs on the negative sphere, and I'm dividing it by 0.30 meters squared. And what I'll get is, again, a fairly simple computation. A negative 2.16 times 10 to the negative 5 newtons, and that's an attractive force. These two are going to be attracting each other because they have opposite signs. Now this next part, if I connect these two spheres with a conducting cable, let's say that I run a cable from these two, and I just connect them electrically. After equilibrium has occurred, find the electric force between the two spheres. So what's going to happen here, because I have a positive 12 nanocoulomb charge here and a negative 18, I see that there is a difference in charge here. And so we are going to get electrons to move between them until we get equal amounts of charge on each object. So that would be what would occur when they reach equilibrium. Now what I'd like to do first is I'd like to determine the total charge. The total charge, if I add these two up, I'll see that I have a negative 6 times 10 to the negative 9 coulombs of total charge. So again, this has more charge than that by negative 6 times 10 to the negative 9 coulombs. So what that means when these two equilibrate and we get the equal amounts of charge in each one is that I'm going to end up moving over this way. I'm going to start sending electrons over here until these each reach a state of equilibrium, which means this is going to end up sending over 15 times 10 to the negative 9 coulombs of charge until this equals negative 3, and this will then be a negative 3 as well. So they'll end up having the exact same amount of charge on them, and they each would have a negative 3 times 10 to the negative 9 coulombs once they reach equilibrium. So now if I want to go ahead and determine the nature of that force. Each one will have the same amount of charge, so they've reached equilibrium. That'd be negative 3 times 10 to the negative 9 coulombs on each. They're still separated by 0.30 meters. And when I go ahead and compute that force now, what I see is that it would now be a repulsive force since they have equal signs, and that would be quite a bit smaller force now, about 9 times 10 to the negative 7 newtons, and again that'd be repulsive. And now this actually shouldn't be written as 2 times 10 to the, or 2 to the 39th. It's really 2 times 10 to the 39. So I don't want to confuse you there with raising 2 to the 39th power versus 2 times 10 to the 39th. So this is the correct answer for that problem. So there's a few examples for you, and that's pretty much it for this section. It's just dealing with the electric force. I'm going to go ahead and go back to this here and let you know that these problems are definitely things that you can and should do for homework. So we'll see you tomorrow. Go Bucks!